that are interested in creating some pipelines for data analysis, and apply this to the upcoming missions, in particular to the XTP and the wide field monitor, since we have our institute heavily involved. So what I want to talk is first the scientific motivation. So what drives my research, of course. Then I will talk a little bit about the wide field monitor that is being developed here in our institute, and then some possible ideas on how to extract efficiently information and create data products from the upcoming and the existing monitoring instrumentation. So as Mar said, I work mostly on X-ray binaries. In particular, I work on low mass X-ray binaries. So for those that don't know, these are systems where you have a neutron star or a black hole here that is accreting mass from a low mass companion star, less than about 1 solar mass or so. And of course, the transfer of mass creates an accretion disk, and this accretion disk generates through viscosity and other processes a large flow of X-rays, and sometimes you also have powerful relativistic jets that are observed. And what I want to explain with in this first part of the talk is why these systems are interesting and how to exploit the data without doing any human intervention. So the first thing is, you know that in these systems, there is a lot of X-ray variability. The reason is because if you calculate the area where the X-rays are produced, the time scales there are very short. For example, one can calculate the dynamical time scale, which scales, I don't know if you see it, but it's just with the radius, so the cube of the radius, square root of the cube of the radius where you are. And so for a neutron star or a black hole, since you can have plasma that reaches almost 2-3 Schwarzschild radii, you can get that the dynamical time scale is of the order of milliseconds. So you expect very slow variations. But you expect also, you expect also slower variations that depend on different parameters in the accretion disk. For example, you can calculate the viscous time scale because the plasma has some viscosity, and this viscosity depends on the radius from of the ring of the accretion disk that you consider and the scale height h of the accretion disk. And of course, there are different physical processes occurring. There is it's believed that there is a hot flow in the inner parts of the system. And if you calculate these time scales, you get something of the order of from milliseconds to thousands of seconds. And if you extend this analysis to the outer regions of the accretion disk, you can get time scales of weeks or months even. So these low mass X-ray binaries have a variety of time scales. And for example, the slowest time scales are the ones that pertain to the so-called transient low mass X-ray binaries. Here you have a system where the accretion disk jumps between states where the accretion disk is fully ionized, where the plasma is fully ionized, and it's very viscous and it produces a lot of X-rays, and states where the disk is mostly recombined, when the hydrogen is mostly recombined, and you have a low X-ray flux. So here, this is a light curve of a binary, and you see all these spikes which occur every few months, and these are the outbursts, and then there are these periods of very low luminosities, which are called quiescence. And if you zoom in one of these spikes, you see the outburst. These are the count rates, and you see that it lasts a few months, let's say, typically, but it can last much less, of course, few days or a few months. There are also systems where you have much longer time scales. These are called the quasi-persistent transients. I mean, again, I'm talking about low mass X-ray binaries here. For example, there are two systems where the time scales are much longer. There's this one, MXB 1659-29, which has outbursts that last for years, and these are called quasi-persistent sources. So this is an example of very long time scale that we can witness. Very recently, there was also the discovery of these systems, which are called transitional millisecond pulsars. These are strange systems that switch back and forth between a low mass X-ray binary state and a radio pulsar state. Here you have the compact object. And at some point, the accretion disk disappears for reasons that are not completely clear. And instead of having emission, a large flow of X-rays from the accretion disk, you get a radio pulsar and with no accretion here. And of course, there are different models that have been proposed for the systems. And the variations here occur on on many orders of magnitude on different timescales. For example, the timescale of this transition is of the order of a few years. This is a system that was discovered in 2007, and it was, sorry, a radio pulsar for about 11 years, and then turned into a low mass X-ray binary, and it still is in this state. And there were archival observations where there were other transitions of the order of a few years. And if you look at the light curve generated during the low mass X-ray binary state, you see a lot of variations in the light curve. This is an XMM Newton light curve in the 0.3 to 10 keV range. And you see that there are all these fluctuations where there is which are very stable, at least in these two luminosity states. There is a very stable low luminosity state that corresponds to luminosities of 10 to the 32 Hertz per second. And then there is a higher luminosity state at about 1 order of magnitude higher luminosity. And it's very stable. And then there are these flares which occur on timescales of a few hours and last for a few minutes only. And so here there are variations of the order of minutes, which are very interesting because some models relate this variability to the viscosity in the accretion disk. Now, low mass X-ray binaries are also have also timescales of the order of hours that occur when there is a transition of state, which is so now I'm not talking about the transitional millisecond pulsar. I'm going back to the low mass X-ray binaries, normal ones. And when they are in outburst, they change spectral states. If you look at the energy spectra of the systems, they switch often between a hard X-ray spectrum, which is usually modeled by Comptonization, as is a power law, and the soft state, which is dominated by soft X-ray emission below 2-3 keV, which is usually believed to be coming mostly from the accretion disk. And during this shift in states, there is an emission of there's a decreation of powerful relativistic jets. So, for example, here these are two what is called the hardness intensity diagrams, where you have the hardness ratio, which is just a ratio between counts in different energy bands, and the luminosity. And basically, what you see is that if you have a black hole accretor or a neutron star accretor, what happens is that during an outburst, these objects track a certain shape, both for both black hole and neutron stars. And then when there's a transition from this region here to this region here, there are radio flares, and you see a jet appear. So this can be detected on timescales of hours. At much, sorry, if you take the light curves, of these objects, low mass X-ray binaries, both with black holes and neutron stars, I mean, there's the known phenomenon of quasi-periodic oscillations. These are basically relatively coherent features that you see in the power spectrum, which are a consequence of oscillations of, or let's say, of variability in the X-rays. You see these features both in neutron stars and black hole accretors. Here on the left, you see 3 examples of power spectra, power density spectra, of black hole accreting binaries. And on the right, you see neutron star accreting binaries. And the range of frequencies that are plotted here are relatively low frequencies, so below 100 Hertz. So here is highlighted as low frequency variability is called, low frequency complex. And these low frequencies don't have these QPOs, these features, these peaks that you see here, don't have a clear explanation, but of course, they are interesting because they are thought to be related, they might be related to relativistic effects. For example, this type C QPO, this frequency here of the order of a few seconds, was proposed to be related to the lens steering precession close to the accretion of this inner edge. And this FBO, NBO, HBO are just nomenclature, but these are similar features that you see in neutron stars. So you have timescales also of seconds, and of course you can go faster than that. You can go to milliseconds, which is the fastest timescale you expect around these systems. And here you see two typical features, which are called the kilohertz QPOs in neutron star accretors, where you see very, very peaked features at hundreds of hertz that can reach up to 1.23 kilohertz. And you see the same features, but at slightly lower frequencies of the order of a few hundred hertz in black hole accreting low mass X-ray binaries. And these are called high frequency QPOs. And these are very interesting because, of course, they are probing the regions which is closest to the neutron star and black hole event horizon and neutron star surface. Because again, this corresponds to the dynamical time. Timescales of milliseconds are also seen in accreting neutron stars when there is a so-called accreting millisecond pulsar. So when you have a neutron star with a strong magnetic field, what you have is that the accretion disk, that is plasma rotating in Keplerian orbits, gets truncated at some location where the magnetic pressure basically becomes dominant over the run pressure. And then the plasma follows the magnetic field lines and hits the surface of the neutron star, forming a flow of soft or hard X-rays if there's componentization at all. And the rotation of the neutron star modulates this X-ray flux. And if you do a power spectrum, you see a very narrow features, which is a delta. This corresponds to a sinusoid at a single frequency in the time domain. So this is the frequency of the neutron star. So here also there's time scale of milliseconds. And finally, you have also thermonuclear bursts and burst oscillations from accreting neutron stars in the mass X-ray binaries. These are very interesting because these are thermonuclear explosions due to basically you trigger the CNO cycle, the same that you have inside stars, or the triple alpha process, and you burn the accreting material in flashes of X-rays. And what you see, it's usually a very peaked X-ray light curve that corresponds to this flash that lasts only for a few tens of seconds. And sometimes what is interesting is that during this explosion, you see what are called the burst oscillations. So if this is time and this is the frequency, so you see this contour plots that represent the frequency of the signal that you're observing, and they usually are observed at a few hundred hertz. And we do know that they are related to the spin of the neutron star. Indeed, about 10 low mass X-ray binaries with the neutron star have a spin known only via the presence of these burst oscillations. And these are usually easily detectable with the power density spectrum. So all this is just to say that all these different time scales from years to milliseconds can be detected, and the data can be exploited by just looking at event data, which means single photons, where you have the energy and the arrival time and so on, and without the necessity of modeling anything whatsoever. So this is just you take the raw data, you do the very quick analysis, you get the information that you are looking for. And so the idea is to write a pipeline so that one can basically take the information in light curves, in energy spectra, and power spectra, and have very little human interaction and process the data and have an alert system to trigger your attention, let's say. Now, we did an experiment like this when back at the time when I was in Amsterdam. And we used this instrument, the RXT PCA. This was an instrument. It was a proportional counter array of the Rossi Xray timing explorer. And for a couple of years, the last 2-3 years of its life, the data became immediately public, so there was no proprietary period. And so what we did is that we built a pipeline. At the time, using these ancient languages like Perl, C, and Fortran. And what we were doing is that this pipeline was checking the website where the data were stored every few minutes, download the data. Then it was applying standard reduction routines that are proper of this instrument. And then with our software, we were creating light curves, power spectra, color intensity diagrams, and so on. And then we were getting emails, all group members were getting emails. And then, of course, we were almost always the first to find something new. And indeed, we published about 20 telegrams. We found a new accreting pulsar. We published 6 papers, basically doing almost nothing actively. This was just by receiving the products of this pipeline. And we used a very strange system, which was whoever sees first the result is the first author. And of course, there were people not sleeping at night. This was a very, very weird way of proceeding. Anyway, it worked because we had sleepless nights. That's a sufficient number of publications and results on top of what everyone was doing, of course. So let's go to the core point that I want to make, which is now here. This is the XTP. This is the announced X-ray timing and polarimetry mission. This is a Chinese-European collaboration. And this instrument, this telescope, will fly 2027 in the United States. And this has 4 instruments. It has the primary instrument, which is called the LAD. And then it has 2 detectors, which will also do polarization. And then there is a wide field monitor. As many X-ray instruments have monitors, but the peculiarity of the wide field monitor is that besides being very good for reasons that I will explain, it's also being developed a lot here, and we have the PI, which is Margarita Hernandez, that is doing is guiding the developments of the instrumentation. This instrument is particularly interesting for 2 reasons. The first one, here on the left, you see the effective area. This is a standard plot that you have seen a million times for different missions. Here it's the LAD and the other instrument, the SFA. And okay, this is the point here is that the LAD, which is the main instrument, is sensitive in between 2 and 30 keV, let's say. It's very, very large effective area. But if you look on the right, this is the sensitivity of the wide field monitor. And here, this is a plot that I took from Inzam et al. I forgot the et al. Here, but there are like 50 people involved. So here you see the energy, and here the peak luminosity. In this case, it was for gamma ray burst detection. And so you can see that the wide field monitor in red reaches basically a sensitivity almost at the bottom, which is good in the sense that can detect the sources that have the lowest luminosity. It's very sensitive, and here it's comparison with other instrumentations that are currently flying or that will fly soon. This is a French mission, I think. Is it? This will fly. A French one, China. Yeah. And another advantage that this instrument has is that has a relatively large collective area. So this is the detector. The detector, the single detector, is basically a coded mask detector. So you have this grid with dark spots and transparent spots where the X-rays can cross, and then you project basically an image of the coded mask on the image plane, and then you can deconvolve it with several techniques and reconstruct the direction from where the source emitted the photons. So this is a very standard way of detecting X-rays and gamma rays nowadays. And the final instrument will have 6 of them in pairs. And if you calculate the total collective area, this is about 1,000 per square centimeters, which is quite huge. Of course, they point in different directions, so your sensitivity will not be with the whole effective area because it depends on where the rays come from. But this gives you a decently high sensitivity for a wide field monitor. It's pretty high. I mean, in comparison, if you take this is the sky. If you take other all sky monitors like the ISM on RXT, I think is 5 times bigger. The 2 cameras that observe the sky, they have 5 times the effective area of the all sky monitor. That leads to a lot of discoveries. Also, the field of view of the wide field monitor is huge. I think it's about 4 steradians or something like that. And whereas other monitors like Maxi have a tiny field of view. There is SwiftBot, which is also flying now, and it has a relatively large field of view, but this is a hard X-ray detector. This is sensitive between 15 and 150 keV. So most of the information that I'm interested in, which is from low mass X-ray binaries, comes mostly below 20, 30 kilo electron volts. And this instrument is also nice because it has an accuracy, spatial accuracy of 1 arc-minute, which is huge. And the resolution is less than 10 microseconds for events data. So you can do timing with this, just with the wide field monitor. Well, this is just a table. I think it's also a bit outdated with different parameters. This is the wide field monitor. This is the effective area at 6 kV. I think this is more 4 than 3. And the only camera that is close to is the one that will fly on this French-Chinese mission. All the others have tiny effective areas. So you expect a very much worse signal to noise. Now, one advantage that we have here is that besides building the instrument, so knowing all the technical details, and beside having the PI here, we are also developing the software for the wide field monitor, the simulation software, I should say, together with the people at Esron and Enough. This is a group that is led by Janet Zandt at Esron. What we are doing is we are trying to make a simulation to understand how to reconstruct the signal of a simulated source. So what we do is that we create source photons according to a physical model, and then you propagate these photons through the instrument, and then reconstruct the image of the instrument. Here you see an example from the paper of Margarita. This is not something that we have done, but this is an example because the 2 cameras are not, to have a 2D positional accuracy, these cameras need to be placed in such a way that they are orthogonal, so that you have a 1.5D image here, a 1.5 image here for the other camera, and then the 2 can give you the position. So we are trying to write this software. So we will be, in principle, here, we will be the first to understand how the data, which kind of data to expect. So how good the data should be, which sources are detectable, which sources are, what is the shape, what all this, what is the instrumental effect, all these kind of things. And so we can use this to, my idea is to build some sort of pipeline to do some automatic data reduction and analysis on the, let's say, similar to what was done back then when we were in Amsterdam. Today, there are several monitoring telescope data, like SwiftBot, Maxi, and so on. So the idea would be, we can, for example, create already a reduction pipeline for this type of instruments to test how they perform. Then we can, this data reduction pipeline will be different, of course, for each telescope, because each telescope needs the specific corrections and the pre-processing. But then the final product is to create light curves, energy, and power spectra. And I'm doing this in collaboration with Manu Linares, that is now in Trondheim, but he was at the Polytechnical University, but still is there. And he was one of the main people behind this RXT PCA adventure that we did back in 2010. And then you have the raw results, and these raw results are either processed via standard analysis. For example, you just check whether there's a peak in the power spectrum, if there is a certain feature in the energy spectrum, and so on. You can send an alarm message to the people. And then my idea was to also explore some machine learning methods to dig a little bit deeper inside the results. Now, a few weeks ago, there was this paper published by Modiano et al., where they did something very similar, where they took the Swift UVOT. This is a ultraviolet and optical telescope on board Swift. And basically, they took the observations from the UVOT. The UVOT has different filters, and then they basically checked the website. They downloaded the website, checked the raw image, and created a pipeline to generate what is called difference imaging. So you have two images that you compare at different times to see whether there are new transits. And what they found is that you can detect pretty easily transients. So this red square here is this part here that you see zoomed in. As you see here, there is a dark spot. Dark spot means simply that in the template image, there was something brighter than in the new image. So there was something that turned off, perhaps. And of course, the problem that they are having now is that they have a lot of artifacts, because when you create these different images, it's very sensitive to the amount of, to the calibration, basically, of your images. So if there are some defects or some strange features in the image, you're going to detect false positives. And so here we, together with Charlie, that is doing a PhD here, we started a collaboration. This was a few months ago, I have to say. Then we stopped because we had a problem with having the raw data, but now maybe we can start again. But together with Charlie, this is an example of what one can do, which is how to distinguish artifacts. So the idea was to create a convolutional neural network model where you look at thousands of images, where you have real transients and you have artifacts, train the model, and basically flag the false positives, hoping to reach a certain accuracy, say above 90% or so. Another thing that another thing that I'm exploring at the moment is this architecture that is called transformers. Now, I don't have a lot of time, but I want to say something very brief. So this is, there are techniques taken, borrowed, if you want, from the area of natural language processing, which are very relevant for us, especially if you look at data in form of a time series, because natural language processing is basically the understanding from machine point of view of the text that you provide as an input. So the machine tries to understand, of course, if you give this sentence, the FBI is chasing a criminal on the run, this is just a gibberish for a machine, doesn't mean anything. So the machine needs to understand what is the structure. And of course, words don't mean anything, they need to be translated into numbers. And numbers need to be translated into some form of encoding of the information of that word inside this number representation. And since sentences are made by sequences of words, you can do something similar by removing the words altogether and basically training your model in such a way that it's the numbers, the sequence of numbers now that need to be represented in the machine learning model. And these transformers were pretty revolutionary in 2017 when it was published by these Google engineers, because they got rid of several of the, let's say, typical architecture that were used before, and introduced this concept of attention. In other words, you see here this blue shaded blue part. Basically, what the machine does is that it processes the information sequentially, and then switches its attention on specific parts of the text where there is more meaning according to this number representation that you have. For example, here at the end, this is what you also do. If you read a sentence, and then at the end of 3, 4, 5 sentences, you know what you read, but if I ask you to repeat exactly the sequence of words, you have no idea. And what you remember is the meaning of those sentences, because you focus your attention on certain parts. And so here there is this mathematical technique, let's say, that makes the machine focus at the end of this process. It focuses on chasing criminal runs. So these are the three important words for this sentence. Now, this was applied last year by these two people, Allen and McEwen, and they applied this on a data set for the Vera Rubin Observatory. So, you know, the Vera Rubin Observatory will observe millions of sources every night. It's an optical Xray survey. And to prepare for the upcoming data sets, there is a public database where there are different type of light curves generated with simulations. And so these people took the hundreds of thousands of time series. They modified the architecture of these transformers. Instead of using words, to use numbers, the light curves in this case. And then they predicted which type of source they were observing according to certain ground truth that they had. And what they found, this is the confusion matrix, where you see what the actual class was versus the predicted one. And they had a quite strong rate of good predictions, except in this case and these other two. They claim it's because they have very few examples. But they reached almost 90% on average accuracy in predicting what type of source they had just by looking at the data. So what we could do is to repeat something like this. What?
How long did they take to get the results? Did they say anything?
I forgot the time, but they used only a V100 GPU. So, and they had to retrain from scratch. So I don't think they spent so much time, because with the one GPU, I forgot now, but probably they mentioned it. But this is something that, let's say, depends on the level of accuracy you want to reach, of course. Now, I forgot to say, this is a good point of Vanessa in the sense that when you look at this type of models, what you take is well, this type of architecture, I should say. You take a model, a pre-trained model from some big company, usually Google, Facebook, that have huge computational power. They train this model, which means they calculate the weights in the neural network, and then they give the weights to you so you can download their model, and then retrain it, but only fine-tuning some parts of the network. And for example, a large model that was trained 2 years ago, I think, from OpenAI, which is a company from Elon Musk, I think. They spent 12 million euros just to do training. And then they realized that they made a mistake. And they said, okay, doesn't matter. This is the model. So that's called GPT-3. There was a data leakage in the test set. Okay. So it's hard to do something that reaches that level of accuracy that this type of companies can do. But because there is very little data exploration and application in our field, even doing something simple like the one that Alan Jr. and McEwen did might give already results which might be better than standard techniques, because the problem of classifying objects, we have hundreds of unclassified objects in many different surveys. So it's if you can reach a level of 90%, that's not bad. Well, for example, one idea that I had, but perhaps is a bad idea, I don't know yet, is to take a Swift bot. This is a monitor that has been going on since early 2005 or so. And there are thousands and thousands of data points for about 1,000 sources. So perhaps we could do something similar to what they did here, but with real data. I actually started to write, I wanted to show you something that I didn't manage, because the problem with this telescope is that most of these data points that you see, this is the counts flux and time. This is a random source. This is B404 Cygnus, which is a very bright black hole transit that was seen in 2014. But then most of the time you see non-detection. So these are mostly zeros. There's nothing, because it's not very sensitive. This is also a coded aperture mask. But the problem is that this is sensitive from 15 kilo electron volt upward. So there's not a lot of signal from X-ray binaries. So I tried to do some classification, and I didn't reach something amazing because most of the times this light curves have zero. So perhaps we should simulate some, I don't know, but let's say this could be a place to start looking into real data to see how this, I forgot to say that these people mentioned in the paper that they would put their code publicly after publication. So I clicked, not found. So I have to write them. Maybe I did something wrong or they found some mistake. I don't know, but it would be interesting to investigate further. Okay, so the conclusion of this is that I'm trying to create this group. So far, there's only me and Manu interested. You don't need to, if you're a student or a postdoc, you say, well, 2027 looks far beyond my career horizon. That makes it interesting, but we can apply this to existing data, telescopes, to detectors, to different wavelengths. And of course, the dirty part is to reduce the data, but that will be done by man, so who cares? We can do the funny part, which is to explore these algorithms, because of course, I'm not even sure that they will outperform or they will be useful in certain areas, but because there's very little investigation in this field, I think it's worth trying. And then in the future, apply this pipeline to new data from the wide field monitor and be the first to basically extract the information in an optimal way from this instrumentation. And that's it. So you can contact me if you're interested. Thank you for your attention.
Thank you, Alessandro. Time for questions?
Two questions. One is serious. And when you say you want to apply, for instance, to the power spectrum,
yeah.
So with machine learning, what would you learn more than with standard analysis?
Depends, because
the question is just
it depends because
how you prevent of having sleepless people.
No, sleepless people is out of question.
Could you repeat the question?
So Daniela is asking if I apply machine learning methods to things like power spectra, what would be the advantage over classic techniques? I can tell you something very quickly. For example, in forgot now, 2009, I saw a QPO. It's called 1 Hz QPO, which is a relatively narrow feature in the power spectrum that corresponds to probably some plasma instability at the disk magnetosphere boundary. Okay, so we published the results. And then we had to go through thousands and thousands of other power spectra by hand because this feature becomes broad. These features change over time. So this feature becomes broad. And by high, you need to be trained in the sense that you have to see these features for 1,000 times to recognize them. And then, because I had the trained eye, we found a new 1 Hz QPO, much broader and weaker in another source. And I was the only one in the Amsterdam group to recognize this, which tells you something, because these people have seen millions of power spectra from the dusk till dawn. So that's to say that the machine learning might learn features that otherwise you need to observe with a long training, human training, and very tedious checking of. So, of course, if you have a very peaked kilohertz QPO, nothing. There's nothing you can, or pulsation, there's nothing a machine learning might add.
Maybe connected to what I asked earlier. So when you say in real time, I guess you assume that you've trained your network, as you explained earlier. So the inference step is probably the thing that you want to be relatively quick.
Yes.
So how quick was this in the original pipeline that you mentioned?
Sorry, again,
how quick was the actual feedback that you got from the pipeline in the original bit? Because I guess that's what you want to target.
That one was very quick because each observation was the order of 1 hour, and then this hour took few minutes to analyze, and then the data products were sent by email immediately. In this case, of course, the bottleneck might be some very slow inference from some very complicated machine learning model. So that would not be near linear time, but the standard analysis is pretty quick, because if you take segment, of course, depends on computational power and much data, because the wide field monitor will have pretty big data flow. So depends also, the computational power you have. I don't know at the moment, so it's hard to say. We need to estimate also how much data you expect. I don't know. Do we know what would be the amount of data expected in terms of bytes? Yeah, there's about, one can check.
We have a couple of questions from Zoom. Barbara is asking, can machine learning be used to predict state transitions in Xray binaries?
I don't know, maybe. I don't think people have looked much into this. I've seen very few. I mean, there are few people that have published mostly classification like that. But in this case, would be some sort of forecasting, time series forecasting. So you look at the spectrum and then you try to predict what will happen next. I don't think has been explored. Probably depends on. I mean, it's hard to say in the sense that it depends on which model, on which architecture one uses to do these things. In principle, yes, but until you, that's why I want to do this, because there's very little. I mean, there's huge room for exploring this area.
We have Konstantinos.
Konstantinos? Can you ask? Or maybe you can read that.
Feedback. What is the what's here? Yeah, read it. It's gone. I don't see. You got that? No. Oh, here.
Okay, no, in the end, he got the question in the end.
Yeah, should I read it? Hi, Alessandro, are you going to employ the same triggering technique to polarization data as well? I suppose unsupervised methods are necessary there since it's vastly unexploited regime. Also, I'm interested to join forces. Okay, for polarization, I cannot tell because this polarization is developed by, these two instruments are developed by Chinese scientists. And I don't know what's their data policy. Do you know if the data will be for the SP? It's not very, we don't know yet. So polarization comes from these two other tasks. There's the land, SPF, and wide field monitor. And so for the polarization, yeah, I cannot tell. But yes, if you want to join forces, we can certainly explore.
Okay, just thank you. Any other questions? There are no more questions yet. Then I think we can leave it here. Thank you so much, Alessandro.
Thanks for you.